A 2-ton vehicle hurtling into a corner at 60 miles per hour generates immense lateral and vertical forces. The suspension acts as the primary mechanical interface, managing how these loads are transferred through the chassis and into the tires. Strip away the body panels, the engine block, and the cabin, and you are left with a dense, highly intricate web of control arms, linkages, and pivot points. This network is not a collection of independent components. It is a strictly coupled kinematic system. The position, angle, and arc of every single control arm mathematically depends on the exact placement of all the others. Because of this tight physical integration, adjusting a single mounting point to correct one handling issue instantly triggers a chain reaction, altering the geometry of the entire assembly. This creates a severe engineering bottleneck. How do you optimize a system where changing one variable simultaneously forces every other variable to shift? Attempting to calculate the exact physical path of these interacting linkages through intuition or mental math is impossible. Achieving precise handling requires deterministic, highly accurate geometric calculation. Historically, engineers had to rely on a brutal trial-and-error process. They cut metal, welded control arms, built physical prototypes, and bolted them to dynamometers or took them directly to the test track. Every single iteration of a mounting bracket or a revised lower wishbone required expensive machining and ate up weeks of development time. Budget and scheduling constraints strictly capped the number of physical layouts a team could actually build and evaluate, meaning they often had to commit to a design path long before exploring better alternatives. Without the ability to see inside the kinematic arcs in real time, teams were left relying on manual measurements on the shop floor, using simple tools to deduce why a car was underperforming after it was already assembled. In today's automotive market, the months required for this physical trial and error can push a vehicle's launch past critical deadlines, threatening the entire project. Relying solely on physical prototyping forces engineering teams to settle for a setup that is merely functional, leaving significant performance and safety potential unrealized. To solve this, we move into a digital environment. This diagram illustrates the foundational rule of vehicle dynamics, maintaining the tire's physical contact patch with the road. The wheel sits here on the horizontal line, next to two floating nodes that represent the chassis. We connect the chassis to the wheel hub using basic upper and lower control arms, forming a simple kinematic chain. The angle of this wheel relative to the vertical axis is called camber. Dialing in a specific degree of negative camber tilts the top of the tire inward, which helps brace the contact patch against the pavement during hard cornering. But a vehicle is never static. As the suspension compresses over bumps or during weight transfer, the control arms pivot, forcing the camber angle to change. This graph tracks that exact angular shift against vertical travel, plotting what we call the camber curve. A poorly calculated curve allows the tire to roll onto its edge, drastically reducing grip. An optimized curve aggressively manages the angle, keeping the rubber flat against the road regardless of chassis compression. To achieve that precise curve, engineers calculate exact lengths and mounting angles for both the upper and lower control arms. While a static alignment provides a necessary baseline, it is insufficient on its own. A car set up perfectly in the garage will see its geometry shift significantly the moment it begins to move and articulate. Suspension engineering is not about holding parts perfectly still. It is the strict mathematical management of geometric change over a specific range of motion. Maintaining the camber curve is only one layer of the problem. A vehicle must also steer. We add a horizontal steering tie rod linkage to connect the steering rack to the wheel hub. Now the conflict begins. If an engineer moves a chassis mode slightly to improve the camber curve, the length and pivot arc of the control arms shift. Because the control arms moved but the steering tie rod did not, their pivot arcs no longer notch. Now when the suspension compresses, the tie rod pulls on the hub, forcing the wheel to steer itself without any driver input. This severe handling flaw is known as bump steer. The geometry also determines the vehicle's roll center, the imaginary point in space around which the entire chassis leans. By projecting lines outward from the upper and lower control arms to their intersection point and dropping a line to the center, we locate this critical node. As the suspension articulates during a turn, this roll center moves. If it migrates too far or too rapidly, the rate of weight transfer becomes erratic, destabilizing the car. This creates a geometric trap. Moving a linkage to correct the bump steer issue will almost certainly pull the roll center out of position. Factoring in caster angles and kingpin inclination pulls these calculations out of a simple two-dimensional plane and into a complex three-dimensional volume. This gridlock of interdependent variables means a single manual adjustment cannot solve the whole system. Calculating all outcomes simultaneously makes digital simulation an absolute engineering necessity. By migrating these calculations into virtual environments, digital simulation platforms like vSUSP collapse the iteration cycle from weeks to milliseconds. Engineers translate physical dimensions into a parametric digital twin. This interface shows the complete suspension wireframe on the left, paired with live numeric outputs on the right. When a designer drags a single mounting node, the software recalculates the entire chain in real time. This instant feedback loop allows engineering teams to evaluate dozens of distinct geometric configurations before a single piece of steel is cut or welded. Access to these sophisticated calculations democratizes vehicle dynamics, giving independent builders and students the exact same analytical rigor utilized by major automotive manufacturers. Digital kinematics front-loads the iteration process, allowing engineers to resolve major kinematic conflicts and optimize behavior before they ever reach the fabrication shop. In collegiate motorsport programs like Formula Student, this kinematic optimization dictates track performance, allowing teams to extract maximum mechanical grip from strict design parameters. Students physically test the digital geometries they built, sitting directly in the chassis they engineered, and confirming their mathematical theories against real-world lateral g-forces. Electric vehicle startups face heavy packaging constraints, forced to build functional suspension geometries around massive floor-mounted battery packs that dictate exactly where control arms attach. Across all these industries, the best practice remains consistent. Lock in and validate the geometric theory early in simulation, and then strictly combine those digital findings with harsh physical track testing to ensure accuracy. Simulation platforms empower designers to parse the massive density of kinematic variables quickly, turning structural complexity into a direct competitive advantage. In the modern automotive landscape, successful vehicle dynamics no longer start on a fabrication bench. They start entirely in the digital realm.